I want you to imagine something for a moment. Um, Picture yourself packing your bags for like a late-season ski trip in the Northeast.
Okay.
You are pulling out your heavy coats, your thermal base layers, your insulated
Are
gloves.
you getting ready for the cold?
Exactly.
Well,
Because the temperatures outside are persistently below normal. And the climatological data from the National Oceanic and Atmospheric Administration, or NOAA, shows it's expected to stay that way right through the end of March.
yeah, it feels like the absolute dead of winter.
It really does. So you zip up your suitcase, you sit down on the couch, and you flip on the television to catch the morning updates. And what you see on the screen makes absolutely no logical sense.
Not at all.
You're looking at footage of chest-high, churning floodwaters, completely washing away critical roadways in Hawaii.
Mm-hmm.
And then the news anchor cuts to a live weather station feed from Arizona. The temperature gauge is reading an astonishing 112 degrees Fahrenheit.
Which is just staggering.
It's wild. The weather map feels like it has been turned completely upside down. You are watching three distinct, violent seasons playing out simultaneously across the same country.
Yeah, it's a massive atmospheric collision.
Welcome to Meteorology Matters, the podcast that dives deep into the science, chaos, and stories behind the weather that shapes our world.
This show was created by meteorologist Rob Jones.
Now, let's get into today's episode of Meteorology Matters.
So today we are looking at a massive stack of recent meteorological research.
Right, and structural engineering reports on Pacific hydrology, along with some rapid climate attribution studies.
Our mission for today's exploration is to understand the invisible atmospheric machinery connecting all of this.
Yeah, connecting a freezing Northeast, a drowning Hawaii, and a baking Southwest.
Because the raw numbers emerging from the American Southwest right now, they're not just unusual.
No, they're not.
They are fundamentally rewriting the established meteorological record books.
I mean, we are looking at observations from places like Martinez Lake, Arizona, Fort Yuma, Arizona, Buttercup, California, Squaw Lake, California.
Right.
All of these locations hit exactly 112 degrees Fahrenheit.
Yeah. And for those tracking the data internationally, that is 44.4 degrees Celsius.
And this happened on March 20th.
Right. And to truly comprehend the magnitude of that number, you must examine the historical context of temperature data collection in North America.
Okay, let's unpack this. What was the previous baseline?
Well, prior to this specific atmospheric event, the highest temperature ever reliably recorded in the United States during the month of March was 108 degrees.
108.
Yeah. And that previous record was established way back in 1954 down in Texas.
Wow. Okay, so look, breaking a weather record by a fraction of a degree, that is a notable event.
Sure.
But breaking a 70-year-old national record by 4 full degrees, that is an absolute statistical anomaly.
It really is. I mean, we are not looking at a single malfunctioning weather station sitting too close to a paved parking lot in the desert.
Right, this isn't a localized fluke.
Not at all. We are looking at recent meteorological research confirming that 8 different states have broken their all-time March heat records.
8 states?
Yeah, just during the life cycle of this single high-pressure system, the spatial footprint of this heat dome is staggering.
It's covering hundreds of thousands of square miles.
Exactly. But the most illustrative data point regarding the intensity of this system is actually found at a much higher elevation.
Oh, you're talking about Flagstaff.
Yes. We need to look at the data from Flagstaff, Arizona.
Right. So for context, Flagstaff sits at an elevation of roughly 7,000 feet. It is the gateway to the Grand Canyon.
It's surrounded by ponderosa pine forests. It's normally quite cool.
Exactly. But during this event, Flagstaff hit 84 degrees.
Which is wild.
They demolished their previous all-time March record by 11 full degrees.
11 degrees.
Yeah. I mean, when a record is broken by 11 degrees, the historical baseline is no longer acting as a reliable predictor.
Right. And it gets crazier. That temperature of 84 degrees in March actually beat Flagstaff's all-time record for the month of April, too.
Wait, really?
Yeah, it beat the April record by 4 degrees.
Oh, wow.
It is a complete temporal displacement of the seasons. The atmosphere is producing late May or early June temperatures before the spring season has officially even begun.
Yeah, because the timing is the most critical factor here. These record-shattering temperatures occurred at the very end of astronomical winter.
Right.
The vernal equinox, which, marks the official astronomical start of spring,
Yeah.
happened on March 20th.
Exactly.
So these 112-degree readings are technically happening in the winter season.
Yeah, winter heat.
So what are the physical mechanics required for the atmosphere to produce that kind of heat in March? It requires a deep explanation.
It does. So basically, we are dealing with a massive ridge of high pressure. And in atmospheric science, meteorologists measure the strength and intensity of these high pressure ridges by looking at specific pressure levels high above the surface.
Right. You don't just look at the ground.
Exactly.
Yeah.
Specifically, we look at the 500 millibar height. And for this particular event, the 500 millibar height maxed out at 598 decameters.
Okay, let's break down the physical reality of those measurements for everyone listening.
Sure.
Why do meteorologists focus on the 500 millibar level, and what does a height of 598 decameters actually look like in the sky?
Well, atmospheric pressure at sea level is roughly 1,000 millibars.
Okay.
As you go higher into the sky, the pressure decreases because there is literally less air weighing down from above.
Makes sense.
So the 500 millibar level is incredibly important because it represents the exact halfway point of the atmosphere's mass.
Oh, I see.
Yeah. Half of the Earth's atmosphere lies below this level and half lies above it. So meteorologists launch weather balloons radiosondes twice a day from stations all over the world to find out exactly how high off the ground this halfway point is.
And the height of that halfway point changes based on the temperature of the air, right?
It changes drastically. Cold air is dense and compact.
Like it shrinks.
Exactly. When the air mass is brutally cold, the 500 millibar level might be found only 5,100 meters off the ground.
Okay.
But warm air expands. When an air mass heats up, it literally pushes the upper layers of the atmosphere higher into space.
So it inflates like a balloon.
Yeah, exactly. So when the weather balloons were launched during the Southwest Heat event, they had to travel 5,980 meters or 598 decameters before the pressure dropped to 500 millibars.
Wow. So that height indicates a column of air that is exceptionally warm, dense, and expansive.
Yes. Statistically, a ridge reaching 598 decameters in March is 3.5 to 4 standard deviations above the climatological normal.
3.5 to 4 standard deviations?
Yeah. If you visualize a bell curve of historical weather data, the vast majority of normal spring weather falls right in the middle bulge of that curve.
Right, the fat part of the bell.
Exactly. An event that is 4 standard deviations away from the mean is sitting at the absolute razor-thin microscopic edge of the curve.
It is an extreme, unprecedented outlier.
Totally.
And the human impact of an atmospheric outlier of this magnitude is immediate.
It's not just numbers on a chart.
No. We are looking at data showing more than 18 million Americans were placed under extreme heat warnings simultaneously.
18 million.
18 million people waking up in the final days of astronomical winter to lethal peak summer conditions.
And, the societal infrastructure, the economic rhythms, and the biological rhythms of a city are simply not calibrated for that kind of environmental shock.
Right. Consider the greater Phoenix area, commonly referred to as the Valley.
Sure.
March in Phoenix is traditionally a massive destination for outdoor events, specifically weddings.
Oh, yeah, it's peak wedding season there.
Exactly. People book these venues years in advance because the historical climatological data promises beautiful, mild, 75-degree weather.
Right.
But instead, you have thousands of couples and event planners forced into frantic, incredibly costly last-minute venue changes.
Because you can't be outside.
No.
Mhm.
It is physically dangerous to be standing outside in a dark tuxedo or a heavy layered gown when the ambient air temperature is baking at over 100 degrees.
Yeah, the human body is highly susceptible to heat illness when forced to endure direct solar radiation at high ambient temperatures without any acclimatization period.
Exactly.
And the disruption extends far beyond weddings. It impacts construction schedules, agricultural harvesting, and the basic operational capacity of the municipal power grid.
Right. And EPA guidelines specifically warn about exposure risks for outdoor workers under these kinds of sudden extreme heat loads.
Absolutely.
But as oppressive and disruptive as this heat is, it is not acting as an isolated local phenomenon.
No, it's all connected.
Right. This massive, expanding high-pressure dome over the American Southwest is deeply mechanically connected to other events happening across the globe.
Yeah.
To truly understand why the western United States is baking like a desert furnace, We have to look thousands of miles across the Pacific Ocean.
We really do.
We have to examine a state that is actively drowning under a catastrophic volume of water. We have to look at Hawaii.
What's fascinating here is the sheer contrast. The situation currently unfolding on the island of Oahu is a full-scale state of emergency.
Yeah, we are seeing catastrophic, rapid onset flooding. Emergency management officials are labeling this the worst flooding event the state has witnessed since the early 2000s.
The sheer volume and intensity of the rainfall are overwhelming both the natural topographical drainage basins of the islands and the artificial human-engineered infrastructure simultaneously.
Let's talk about the human toll of that overwhelmed infrastructure. We have reports of over 230 swiftwater rescues taking place.
Over 200, that's
Yeah.
massive.
Think about the jarring contrast of that reality. On the West Coast, you have emergency rooms treating patients for severe heat exhaustion and heat stroke.
Right.
Simultaneously, in Hawaii, first responders are utilizing boats and helicopters to pull people from rising, churning floodwaters. Roughly 10 individuals have been hospitalized for hypothermia.
And hypothermia in a tropical climate like Hawaii really underscores the severe and prolonged nature of the exposure.
Yeah, how does that even happen there?
Well, when the human body is submerged in fast-moving floodwaters, heat is drawn away from the core exponentially faster than it is in cold air.
Wow. And the focal point of the danger on Oahu right now, the specific crisis keeping civil defense managers awake at night, is the Wahiawa Dam.
Yes, the Wahiawa.
This is a massive earthen structure that is 120 years old. The emergency alerts coming from state officials indicate the dam is at imminent risk of failure. Water is actively, uncontrollably running over the emergency spillway.
Right, and the Wahiawa Dam represents a critical vulnerability in the historical infrastructure of the region.
How so?
Well, Hawaii possesses 132 state-regulated dams, and a significant portion of these structures, including Wahiawa, were not designed using modern hydrological modeling,
Okay.
nor were they built to withstand the rainfall rates we are seeing in the current climatological data. They were constructed more than a century ago, primarily to support the massive irrigation needs of the sugarcane industry.
So they were engineered to capture and hold steady, predictable, seasonal rainfall for agricultural use.
Exactly.
They were absolutely not engineered to serve as flood control monoliths against the kind of catastrophic, concentrated deluge we are watching unfold today.
Right. And when a century-old earthen dam reaches its maximum capacity and the emergency spillway is fully engaged, the structural integrity of the entire embankment is tested to its absolute physical limits.
Because it's just dirt and rock, basically.
Exactly. An earthen dam is essentially a massive, highly compacted mound of soil, clay, and rock. If the water overtopping the spillway begins to erode the downstream face of the dam, a process known as headward erosion, the structure can unravel and fail with terrifying speed.
And the authorities on the ground are acutely aware of that physics. We are seeing literal leave now evacuation orders sent in all capital letters pushed directly to the mobile phones of over 4,000 residents in the downstream communities of Waialua and Halewa.
Yeah, the warning language being utilized by emergency managers is incredibly stark.
They are explicitly citing the threat of life-threatening, fast-moving water. If the Wahiawa Dam breaches, we are looking at a catastrophic, instantaneous release of millions of tons of potential energy.
Because a catastrophic dam failure does not just release water, it creates a high-velocity debris flow.
Right.
You are talking about a towering wall of mud, uprooted trees, destroyed vehicles, and pulverized infrastructure moving rapidly through densely populated residential areas. The destructive force is absolute.
And the visuals coming out of the rescue operations are already harrowing. The National Guard has been fully deployed.
Yeah, I saw that.
In one instance, they had to utilize heavy-lift helicopters to airlift 72 children and adults from a spring break youth camp.
72 people.
Yeah. The floodwaters rose so rapidly and with such intensity that all terrestrial exit routes were completely severed.
Wow.
You have communities dealing with chest-high, incredibly toxic muddy water inundating their living rooms. Critical arterial roadways have been completely washed into the sea, severing supply chains.
It's devastating.
We are looking at millions of dollars in damages to residential and commercial properties. The crisis even extended to a major medical facility on Maui, which sustained such extensive water damage that emergency protocols had to be enacted to relocate vulnerable patients.
And the logistical complexity of evacuating a hospital during a severe flood event is immense.
I can't even imagine.
Moving intensive care patients who are dependent on ventilators and continuous intravenous medications down flooded, impassable streets strains the municipal emergency medical response apparatus to the breaking point.
Okay, so we have established two absolute terrifying extremes.
Right.
We have a 120-year-old earthen dam pushed to the brink of failure, resulting in hypothermia rescues in the flooded streets of Hawaii.
Yes.
Simultaneously, we have 112-degree, record-shattering, lethal heat baking the deserts of Arizona.
Mm-hmm.
And hovering in the background of all this, we have a freezing, persistently below normal weather pattern locked over the Northeast.
Right, the third piece of the puzzle.
Stop.
Yep.
Are you looking at the climatological data and telling me that catastrophic rain in Hawaii is actively, mechanically creating heat in Arizona?
Yes.
That defies basic thermodynamics from a layman's perspective.
Mm-hmm.
How does freezing wet water falling from the sky in the middle of the Pacific Ocean generate thermal energy that bakes a desert 3,000 miles away?
If we connect this to the bigger picture, it sounds entirely counterintuitive, but it is one of the most powerful physical processes on the planet.
Okay, lay it on me.
To understand the mechanism, we have to look closely at a specific atmospheric feature sitting over the Hawaiian Islands called a Kona low.
Kona low?
Yeah. A Kona low is a type of seasonal subtropical cyclone that draws massive amounts of deep, incredibly rich tropical moisture northward from the equator.
Okay, so we have a massive swirling storm pulling ocean water into the sky.
Mm-hmm.
Where does the heat come from?
The heat is generated through a process called the phase change of water.
Phase change.
Right. When solar radiation hits the ocean surface, it causes liquid water to evaporate into water vapor.
Sure.
But evaporation is a cooling process. It takes energy, specifically heat energy, to break the molecular bonds of liquid water and turn it into a gas.
Okay, that makes sense.
But that heat energy does not disappear. It is stored inside the water vapor molecules as they rise into the atmosphere. We refer to this stored energy as latent heat.
Wait, so the sky over Hawaii is filling up with trillions of gallons of invisible water vapor, and every single molecule is carrying a tiny battery of stored solar heat.
Precisely.
Wow.
And when that massive concentration of water vapor is forced upward by the Kona low, the air cools and the vapor condenses back into liquid rain.
Okay.
When water vapor condenses, the physical process runs in reverse. All of that stored latent heat, the energy that was required to evaporate the water days or weeks prior, is violently released directly into the upper levels of the surrounding atmosphere.
The sheer act of raining catastrophically over Oahu is acting like a massive invisible furnace, pumping thermal energy into the upper troposphere.
That is the exact mechanism.
That is unbelievable.
And that massive plume of newly released latent heat does not simply linger over the Hawaiian Islands.
It goes somewhere.
Yes, it is immediately captured by the upper-level wind currents. A powerful atmospheric river, a narrow, highly concentrated corridor of moisture and thermal energy, begins to act like a planetary-scale conveyor belt. It shunts that latent heat rapidly northeast, driving it directly toward the Pacific Northwest coastline of the United States.
So when that high-velocity conveyor belt of heat and moisture slams into the North American mainland, what is the physical reaction?
The atmospheric river diverges upon impact with the continent. A significant portion of that kinetic and thermal energy is forced to run south.
South, towards the desert.
Exactly. It actually feeds directly into the upper-level circulation of the high-pressure dome sitting over the western United States. The catastrophic condensation and rainfall in Hawaii is actively, continuously pumping thermal fuel into the exact high-pressure system that is baking Arizona and California.
That is wild. The drowning of one state is quite literally providing the thermal energy to bake another state.
Yes.
You could not engineer a more tightly coupled, highly efficient system if you tried. Usually when we think of deep moisture and heat flowing into the United States, we picture the Gulf of Mexico pumping humidity northward up into the Great Plains.
Right, that's the usual pattern we discuss.
But in this specific scenario, the Pacific Ocean is running the entire continental show, dictating the severe weather parameters for millions of people across multiple time zones.
And this interconnectedness is driven by planetary-scale atmospheric waves, specifically Rossby waves.
Rossby waves, right?
Yeah. The atmosphere is a continuous fluid envelope that constantly seeks a state of equilibrium. It achieves this balance through massive, undulating waves of pressure. There is a principle in fluid dynamics known as the conservation of absolute vorticity.
Okay, let's translate the conservation of absolute vorticity for our listeners. Let's step away from basic analogies and look at the actual physics of the sky.
Think of the classic physics example of an ice skater spinning on the ice.
Okay.
When the skater pulls their arms in tight to their body, they spin much faster to conserve their angular momentum.
Right.
The atmosphere follows similar rules on a planetary scale. When the jet stream is forced to make a massive, violent bulge northward over the western United States, creating our heat dome, the mathematics of vorticity dictate that the airflow cannot simply level out.
It has to react.
Yes. The atmosphere must compensate for that massive northward displacement by plunging deeply southward downstream.
And that deep compensating plunge downstream is the deep trough of low-pressure funneling freezing Arctic air directly into the Northeast.
Exactly. The intense ridge in the west mechanically requires the deep trough in the east to exist.
Wow.
And the energy fueling the ridge in the west is being supplied by the latent heat release from the Kona Low in Hawaii. It is a single, continuous planetary engine operating at maximum capacity.
It's like the atmosphere is a giant water balloon. If you press down on the East Coast, bringing all that cold air south, it forces a massive bulge up in the west, which is the heat dome. And that creates ripples all the way out to Hawaii. It is a completely interconnected planetary engine.
That's a great way to visualize it.
So let's focus our attention back to the specific anatomy of the heat dome itself. The term summer-like ridge keeps appearing in the recent meteorological research to describe a weather event happening in the final days of March. What makes the internal architecture of a high-pressure ridge so incredibly oppressive?
Well, the primary mechanism operating inside a heat dome is a physical process called subsidence.
Subsidence, okay.
Ridges of high pressure are vast mountains of air in the upper atmosphere, and air fundamentally wants to flow from areas of high pressure to areas of lower pressure.
Right, seeking that balance.
Exactly. High up in the troposphere, air rushes outward away from the center of the ridge. This evacuation of air aloft creates a void.
And nature abhors a vacuum.
Yes. So to fill that void, the massive column of air sitting above the center of the high pressure is forced to sink violently downward toward the surface of the Earth.
And as that massive column of air sinks, its physical properties undergo a radical transformation.
Right. As the air descends, it encounters the increasingly higher atmospheric pressure that exists near the surface of the Earth.
Because the air is thicker down here.
Yes. And this higher pressure squeezes the descending air mass. In thermodynamics, there is a principle called adiabatic heating.
Adiabatic heating.
Yeah. When you forcefully compress a gas, the kinetic energy of its molecules increases, and the gas warms up rapidly.
So the high-pressure system acts as a planetary-scale atmospheric trash compactor.
Ha! Yes.
It is pressing down with immense force on the American Southwest, heating the ambient air to record-shattering levels entirely through the physical force of compression.
That is spot on. And the consequence of that atmospheric trash compactor is a complete and total suppression of vertical motion.
What does that mean for the weather?
Well, the sinking, compressing air creates a highly stable environment. Without upward vertical motion, warm air at the surface cannot rise.
Okay.
If air cannot rise, it cannot cool, and its water vapor cannot condense into droplets.
Which means absolutely zero clouds can form. The sky is swept completely clean.
Exactly. The absence of cloud cover allows the incoming solar radiation to strike the surface of the Earth entirely unimpeded, from the moment the sun rises until the moment it sets.
Just baking everything.
Yes. The soil, the asphalt, and the concrete absorb that intense solar energy and heat up rapidly. The ground then radiates that thermal energy back into the air directly above it.
And it has nowhere to go.
Right. The massive sinking weight of the high-pressure dome acts as an impenetrable lid, trapping all of that heat at the surface and preventing it from escaping into the upper atmosphere. The cycle compounds on itself day after day.
Here's where it gets really interesting.
Yeah.
The biological fallout from this compounding heat cycle is playing out across the country at a terrifying velocity.
Yeah.
We have to introduce a vital scientific concept here called phenology.
Right, phenology. It's the rigorous study of cyclic and seasonal natural phenomena.
Exactly.
It focuses specifically on how climate and weather patterns dictate the life cycles of plant and animal life.
Well, according to the latest climatological data and phenological tracking, spring leaf out, which is the specific biological moment when trees and perennial plants push out their very first green leaves, is currently running 3 to 5 entire weeks early.
Wow. 3 to 5 weeks.
Yes, in places like Colorado, Kansas, and across the vast expanse of the northern Great Plains.
That is massive. The flora of the continent is mechanically responding to the environmental cues it is receiving.
Right.
The unprecedented heat dome is providing the exact thermal signals that trick the vegetation into believing that deep, stabilized spring has permanently arrived.
But the calendar dictates reality. It is still March.
Right.
The vernal equinox just occurred. This massive thermal deception creates the extreme systemic danger of what agricultural scientists call a false spring.
Yes, false springs are incredibly disruptive.
Let's use an analogy of a highly calibrated factory assembly line.
Okay, I like that.
A tree sitting dormant in the winter has a strict chemical budget of energy stored in its root system. It takes a massive expenditure of that stored energy to power up the assembly line, to push sap through the trunk, to swell the buds, and to unfurl the delicate new leaves.
Right.
The tree relies on the gradual, predictable warming of normal spring to ensure that once it spends its energy budget, the solar panels, the new leaves, will survive to begin generating new energy.
Makes perfect sense. But when the heat dome forces temperatures into the 80s and 90s in March, the tree immediately powers up the assembly line and spends its entire chemical budget.
Exactly. The buds open. The delicate water-filled tissues of the new leaves are completely exposed to the elements.
And the tree is now biologically bankrupt and incredibly vulnerable.
Yes. If the atmospheric seesaw shifts in 2 or 3 weeks, if a standard, entirely expected, seasonable April cold front sweeps down from Canada and plunges temperatures below freezing, the water inside those newly exposed leaves will freeze, expand, and rupture the cellular walls.
The biological destruction would be absolute. The initial false spring tricks the plants into gambling their entire energy reserve on the heat dome, and a subsequent normal freeze will annihilate them.
Right.
It destroys the fruit crop for the entire year. The agricultural supply chain for certain commodities can be decimated in a single night of frost following a false spring.
And the danger of this heat dome is not restricted to agricultural collapse. It is profoundly lethally human.
Yes.
Extreme heat is consistently the leading cause of weather-related fatalities in the United States. Heat kills more individuals annually than hurricanes, tornadoes, and catastrophic floods combined.
It's the silent killer.
Absolutely. Hitting 112 degrees in the month of March makes the environment exponentially more lethal than hitting the exact same temperature in the middle of August.
And the danger lies in the physiological mechanics of human heat adaptation. The human cardiovascular system requires significant, sustained time to acclimatize to extreme thermal stress.
Walk us through the exact biological mechanism of acclimatization. What happens to the human body over a normal, gradual spring transition that is failing to happen right now?
Sure. During a normal seasonal transition from spring to summer, as temperatures slowly rise, the human body undergoes a complex physiological shift.
Okay.
The most critical adaptation involves your blood. Over a period of several weeks of gradual heat exposure, your body actively increases its total blood plasma volume.
It manufactures more fluid for the cardiovascular system.
Exactly. It expands the fluid volume without adding more red blood cells.
So the blood gets thinner.
Right. This thinner, higher volume blood is easier for the heart to pump. When you are exposed to high heat, your heart has to pump massive amounts of blood away from your internal organs and push it out to the tiny capillaries in your skin.
Okay, to radiate the heat.
Yes. The heat from your core is transferred to your skin, where the evaporation of sweat can carry it away into the air.
But when you jump directly from cold winter weather into peak, record-shattering summer heat in a matter of hours, that adaptation has not occurred.
Not at all. You have zero acclimatization. Your body is operating with a lower volume of thicker, winter-adapted blood.
Wow.
When the March heat wave hits, your heart begins beating violently, attempting to force this thicker blood out to the skin to cool your core. The cardiovascular strain is massive and immediate.
And your sweating mechanism is inefficient.
Right. Your internal cooling system is completely overwhelmed. This leads directly to heat exhaustion, rapid progression to heat stroke, and, in severe cases, sudden cardiac failure.
And the biological vulnerability is compounded by the vulnerability of our built environment.
Yes, the infrastructure.
In the middle of March, the vast majority of residential homes, apartment complexes, and municipal buildings have not yet prepared their air conditioning units for the summer load.
The necessary seasonal maintenance just has not been completed.
Right. The regional power grid operators have not scaled up their generation capacity to handle peak summer cooling demand. We are throwing a mid-July atmospheric crisis at a society and an infrastructure grid that is still functionally, legally, and economically operating in winter mode.
It's a systemic shock.
So what does this all mean? This systemic shock forces us to address the fundamental question. Why is this precise configuration of extreme events happening now?
It's the million-dollar question.
Right. To answer that, we are going to rely strictly on recent meteorological research. We are looking at the findings of rapid attribution studies regarding this specific, record-breaking Southwest heat wave.
And looking at the recent attribution studies, our goal here is simply to follow the math.
Just reporting the findings of recent research.
Exactly. When researchers run these models, they are looking at pure thermodynamics and historical statistics.
And attribution studies are highly complex mathematical frameworks, right?
They are. They're designed to determine exactly how much of a specific extreme weather event was influenced by underlying documented shifts on global climatological data.
So how do researchers actually perform that calculation? How do you isolate the impact of a shifting climate baseline from the standard chaotic noise of daily weather?
The methodology relies on immense computational power. Researchers utilize decades of high-resolution historical observation data combined with advanced supercomputer-driven climate models.
Okay.
They first simulate the extreme weather event, in this case, the 112-degree heat dome within our current observed climate reality.
The world as it is today.
Right. Then they run thousands of simulations of a purely hypothetical climate model.
What does that hypothetical model look like?
This hypothetical model represents an Earth that has not experienced the well-documented baseline warming of the industrial era.
I see. So they compare the frequency and intensity of the heat dome in the real world against the frequency and intensity of the heat dome in the mathematically simulated unwarmed world.
Exactly. When they compare the two massive data sets, the mathematical divergence is stark.
What did they find?
The research indicates that a heat wave of this specific record-shattering magnitude occurring specifically in the month of March is virtually impossible to produce in the hypothetical models without the underlying thermal shifts present in our current global climate data.
Virtually impossible.
Yes. The researchers classify an event of this intensity within this specific geographical footprint as a 1 in 500-year event.
Okay, let's look at the hard statistical numbers they extracted from the models. The research indicates that a globally warmer baseline of just 1.3 degrees Celsius makes this specific heat event 800 times more likely to occur than it would have been in the pre-industrial baseline.
800 times. The shifting baseline alters the fundamental probability matrix of the atmosphere. But it does not simply increase the frequency of the event. It amplifies the sheer intensity of the heat. The attribution data demonstrates that the 1.3-degree baseline shift has made this specific atmospheric event 2.6 degrees Celsius hotter than it would have been otherwise.
Wow. And that 2.6 degrees Celsius addition is not a trivial margin. It is the absolute difference between a very uncomfortable, sweaty afternoon and a lethal, infrastructure-melting, record-shattering emergency.
It really is.
But the data point that is perhaps the most shocking emerges when the researchers narrow their focus away from the century-long timeline and look exclusively at the last decade.
Right, because the pace of atmospheric change is not linear, it is actively accelerating.
Yes. The data reveals that in just the last 10 years alone, a baseline shift of 0.4 degrees Celsius has made events exactly like this Southwest heat dome 4 times more likely to happen.
In just 10 years.
Furthermore, that shift over the last decade has added 0.8 degrees Celsius of raw heat to the peak temperatures we were experiencing today.
That's incredible.
The parameters of our atmosphere are shifting drastically within the span of a single human decade.
This raises an important question, though, regarding the seasonal distribution of this intensifying heat. You would logically expect the most extreme heat shifts to manifest during the peak summer months of July or August, when solar radiation is at its absolute maximum.
You would think so, yeah. But the researchers point out a fascinating, highly disruptive anomaly in their climatological tracking.
Right. The most substantial long-term warming signal for heat extremes in this specific region of Western North America is not occurring during the summer.
Where is it occurring?
The most aggressive warming trends are manifesting specifically and intensely in the month of March.
Wow. March is warming at a faster rate, specifically at the extreme high end of the temperature spectrum, than the summer months.
Yes. The data shows that typical March peak temperatures have risen by as much as 6 degrees Celsius in certain parts of this region when compared directly to historical 20th century baselines.
6 degrees. We are witnessing a fundamental mechanical restructuring of the seasonal transition period. The atmosphere is no longer producing a gradual, predictable spring.
No, winter is abruptly, violently terminating into peak summer conditions.
And this restructuring brings us right back to the dual crises we are witnessing today. We are watching a slow-motion collision.
A collision of what?
We have an entire continent of aging infrastructure designed, engineered, and built for a stable climate baseline that existed a full century ago, now actively colliding with rapidly shifting, mathematically intensified weather extremes.
Right. Like we talked about, the Waiheoa Dam in Hawaii was intricately engineered for the predictable historical rainfall patterns of the early 1900s.
Exactly.
The earthen walls and the emergency spillway were never modeled to withstand the latent heat-driven atmospheric rivers of today.
And the municipal power grids in Arizona are strictly calibrated and budgeted for extreme heat waves that arrive in late June, not in the final days of astronomical winter. This collision demands that we ask incredibly hard, expensive questions about the future of urban planning and civil engineering.
We really have to.
How do city engineers, state hydrologists, and emergency managers adapt and protect populations when the historical data they use to build their models no longer accurately predicts the future behavior of the weather?
That's the real challenge.
If the data shows that the 100-year flood map is now functionally the 10-year flood map, and the July heat wave is now arriving as the March heat wave, the fundamental blueprints for our cities, our agriculture, and our economies have to be completely redrawn.
It requires a massive societal paradigm shift in how we assess environmental risk, how we allocate municipal funding, and how we build physical resilience into our critical infrastructure.
Right.
We can no longer build for the climate of the past.
We can't. And as we wrap up this exploration of the data today, I want to leave you with a profound new concept to ponder.
Okay.
Think about the basic fundamental structure of the calendar year as we have all been taught it since childhood. Spring, summer, autumn, winter.
Right, the 4 seasons.
Those 4 seasons form the rhythm of human history. They dictate our holidays, our school years, our clothing, and our culture.
Yeah, they anchor us.
But if astronomical winter is now physically capable of producing 112-degree desert days in Arizona and catastrophic 20-year flood events in Hawaii simultaneously, how will our traditional definitions of the 4 seasons need to evolve?
It's a great question.
Will we reach a point where categorizing the year into 4 neat, evenly spaced, predictable segments is no longer meteorologically or agriculturally accurate?
We might.
Will we need to entirely rethink our agricultural calendars? Will a commercial farmer in Kansas or a vineyard owner in California have to plant their crops based on a completely new, erratic seasonal expectation, forcing them to completely abandon the historical almanacs of their grandparents?
They probably will have to.
It is a profound structural shift in how our planet operates, and it is happening right outside our windows in real time.
It really is.
We want to thank you for joining us on this exploration today. Make sure to like, follow, comment, and rate today's exploration. We rely heavily on your feedback to keep bringing you these intense examinations of the data.
And if you want to stay up to date with the complexities of the weather as it happens, you need to follow the creator of this show.
Absolutely. Make sure you follow meteorologist Rob Jones across all of his social media platforms. On Instagram, you can find him by searching Meteorologist. Over on TikTok, search for TV Meteorologist. And on YouTube, hit subscribe on Rob Jones Hurricane.
Right. That is also where you can find the entire Meteorology Matters audio playlist, so you never miss a vital discussion.
The atmosphere never stops moving. It never stops changing, and neither do we. You've been listening to Meteorology Matters, created by meteorologist Rob Jones.
Thanks for listening, and remember, meteorology always matters.